Greetings from Istanbul Technical University. I am Kerem, the team lead of IT Rover Team. We proudly introduce our 10th generation rover, ARC'26 rover. We are ready for the Anatolian Rover Challenge 2026. Established in 2016, our team works in the field of space robotics and specializes in rover science. Since our establishment, we have been pioneers in this field, guiding and supporting other organizations interested in space robotics. We aim to lead and represent Turkey in international competitions. As the IT Rover Team, we have proudly represented our country by bringing multiple international awards back home. Our team competes in 3 major international competitions: University Rover Challenge, European Rover Challenge, and Anatolian Rover Challenge. In 2018, we proudly brought home the Best Science System Award from the University Rover Challenge. Over the past 4 years, we have also earned several recognitions at European Rover Challenge, including the Best Maintenance Task Award, the Best Presentation Task Award, as well as second and third place finishes. Now we are ready to push the boundaries of exploration at the Anatolian Rover Challenge 2026. Our astronauts follow a structured training program that combines technical knowledge with hands-on field practice. They learn how our rover operates, how to communicate with ground station, and how to handle unexpected issues during a mission. For us, a well-trained astronaut is just as critical as well-engineered rover.
The team comprises over 50 active undergraduate students led by a team captain at the top and structured into 6 specialized sub-teams: mechanical, electronics, software, science, design, and organization. To streamline our workflow, rely on Microsoft Teams Planner for both planning timelines and assigning tasks. This platform helps us clearly visualize our responsibilities and deadlines. Our rover is designed, built, and tested in the IT Rover workshop, where all sub-teams collaborate in a shared engineering environment. The workshop provides dedicated facilities for PCB assembly and mechanical manufacturing. After prototyping, each subsystem is individually tested and iteratively improved, then fully integrated and validated through real-world field tests.
Designed for structural integrity, our rover features a robust chassis built on a modular T-slot aluminum framework. The foundation of this architecture is centered on a newly upgraded carbon fiber central tube, which serves as the primary load-bearing spine. To ensure stability across unpredictable topographies, the rover utilizes a rocker suspension system to maintain optimal weight distribution and terrain contact. The drive system is powered by 4 brushless DC motors, securely encased to shield them from environmental hazards. These motors drive our custom wheels, which consist of impact-resistant ABS rims paired with flexible high-traction TPU tires, maintaining a compact and stable footprint. The rover can rotate 360 degrees on its own axis and perform tank maneuvers. Despite upgrades, it measures a 1.1 meter length cube and fully assembled, keeping it well within the competition size and mass limits. The rover is powered by a 42-volt lithium-ion battery that supplies all components. 2 custom power distribution boards manage energy. One directly feeds all BLDC motor drivers, while the other steps the voltage down to 24 volts, 19.5 volts, 12 volts, and 5 volts. The drive system is managed by our rover control unit, which is based on ARM-based microcontroller. This unit not only controls rover's motion, but also manages the status LEDs to provide visual feedback. Additionally, it decodes the RSCP messages used in the competition. The communication is established with motor drivers, various sensors, magnetometer, GNSS modules, computers, and ground station using protocols such as CAN bus, UART, I2C, SPA, as well as Ethernet-based communication over a LAN. All motors are controlled by its own motor driver, and these drivers are connected to each other and to the RCU via the CAN bus network. The RCU coordinates the rover's movement based on the commands received from the ground station or via RSCP. In the drivetrain subsystem, speed control is implemented by using feedback from Hall sensors to ensure stable transfers across harsh terrain. This allows motors to reach target speeds precisely while minimizing speed fluctuations. For the robotic arm, encoder-based position control is used. This structure enables the arm to achieve high-precision positioning, perform complex tasks, and maintain stable and repeatable motion. The manipulation system consists of a high-performance 6 degree of freedom robotic arm engineered to manage a diverse array of payloads exceeding 6.5 kilograms, ranging from delicate electronic components to heavy geological samples. This year, we have unveiled an improved mechanical architecture driven by custom-engineered silo reducers that deliver high-torque transmission with near-zero backlash for fluid, vibration-free motion. The physical structure utilizes a hybrid of carbon fiber tubes and 70-75 aluminum combination optimized to maximize agility and strength-to-weight efficiency while minimizing mechanical stress across the rugged terrains of the Mars and the Moon fields. To achieve high precision, the control stacks employs a closed-loop PID architecture utilizing encoder feedback via CAN-FD bus. The software environment utilizes ROS and MOVE with inverse kinematics to calculate exact joint trajectories for complex maneuvers, with every operation validated through gazebo simulations. Supported by integrated USB cameras for vision feedback, the system's grasping mechanism ensures accurate interaction with complex devices, including opening drawers and placing boxes inside, as well as operating USB Type-A and Type-C connectors, toggle switches, and buttons equipped with safety covers. These advancements guarantee the rover's capacity to overcome complex operating difficulties with high reliability and robustness during field operations. The manipulator's versatility is most evident in its application to specialized mission scenarios. During the night mission, the system retrieves specialized tools to seal fuel leaks via monitoring leak traces and restores life support infrastructure by managing valves and replacing oxygen pipe with a new one. In the collaboration mission, the arm demonstrates dexterity by reading factory reset pins from displays, inputting codes via numeric keypads, also capable of connecting pipes easily to restore vital infrastructure. Beyond the mechanical repairs, the arm easily handles tools like mullets and screwdrivers, and also rock samples. Finally, the arm can operate a brush to paint, allowing Rover to successfully participate in artistic tasks. Designed two distinct emergency switches, both placed for quick and easy access.
Our system guarantees scientific accuracy. The custom shovel processes soil for precise analysis, while the drill securely extracts 15 cm deep samples. The Mars field exhibits the complex magmatic nature of Athabasca valleys. Our exploration targets the habitability of Athabasca valleys, rootless cones, where ancient lava-ice interactions likely created suitable hydrothermal conditions that could support life. We are going to use panoramic and depth cameras which will work alongside our magnetometer to assess the geological formations. This year, our team is applying a geophysical method by integrating a magnetometer system. This system is based on prospecting magnetic field distributions and anomalies. The system works with two separate magnetometers. One of them is mounted on the vehicle for field surveys and the other acquires base station data for more accurate results. Modeling collected data allows us to generate high-resolution magnetic maps of the region. With this ability, our rover can now investigate magnetic properties of geological structures. Additionally, it can be used to detect iron oxides to evaluate habitability and potential microbiological signs. The UV spectrometer is responsible for analysis about our target biomolecules, which perform collaborative work with our test that gives us strong spectroscopic evidence of molecules in question. This system enables quantitative investigation via significant color changes or directly at specific wavelengths. For understanding mineralogy of specific regions, we develop Raman spectrometer, which is a vibrational spectroscopic technique that gives us molecular fingerprints. To overcome fluorescence, a 785 nanometer laser diode with insufficient energy for electronic transition in most cases, photobleaching as physical method and fast-forward transform as computational method are combined. The board system is designed to test the hypothesis that biological signatures and potential habitability, if present, can be reliably detected through a multi-layered approach. Our primary target is glucose, quantified through RGB-based colorimetric analysis using nanoseme and enzyme integrated paper-based systems, validated under controlled laboratory conditions. In parallel, a spectrometer detects riboflavin, ATP, protein, and amino acids on their unique spectral signatures. By integrating these correlated measurements, the system provides a robust and efficient platform for biosignature detection in extraterrestrial environments. The rover's autonomy system pinpoints its precise location and plans its routes using an adaptive Kalman filter and SLAM algorithms. This architecture fuses raw data from RTK, GNSS, IMU, LiDAR, wheel, Hall sensors, and visual odometry to navigate efficiently and prevent collisions. To safely bypass physical obstacles, the system utilizes LiDAR-generated point cloud data to construct a dynamic navigational coast map. During search missions, depth cameras supply essential visual data to rover's custom artificial intelligence algorithms. The system executes a spiral search algorithm to successfully locate and identify RECO markers from a significant distance. RF modules provide robust two-way communication between the base station and rover. On board, dedicated managers arm and drive train translate manual input, move it, trajectories, and autonomous directives into CAN-based motor commands. Simultaneously, and the autonomy manager fuses sensor data for precise mapping, marker detection, and safe route execution. User interface for facilitate the execution of various commands, display of video feeds, and the visualization of the scientific graphs. Communication between rover and the ground station is provided by 5.8 GHz and 2.4 GHz communication modules. All our cameras are encoded via Raspberry Pis to minimize data size, ensuring efficient transmission even in poor radio conditions. In the light of the data, we can see both map and the rover's current location with our user interfaces.